All right, guys, so the next part of the lesson is 2.4, and it's dealing with free fall, which is essentially moving in the y direction. So we're going to drop things or throw things up or do that kind of work. So I'm going to start you off with some questions, and this is an Edpuzzle, but we're just going to kind of watch a YouTube video and make some questions out of it. So let me click on this object, and hopefully it'll take us to what we need to go to. I will skip the commercial as soon as I can, but it is Star Wars. So. Okay. That is not great.
The Stirling engine is an incredible invention.
Sorry. Alright, so we're getting closer. Alright, so the basis of this is we're going to drop a book and a piece of paper and obviously try to make some predictions about what's going to happen. All right, so as you can see, this person has a book in their hand and a piece of paper in their hand. If you want to do this at home, I would suggest you try it. It works perfectly the same way for you as well. But obviously the book is more massive. It's got more matter in it than the piece of paper. And if we were weighing those two things, we would put it on a scale, and the weight of the book would be more than the weight of the individual piece of paper. So I want you guys to make a prediction as to which object is going to hit the ground first. So the book, the paper, or you have the possibility that they could hit at the same time. So I will give you all three options and let you pick now. So let's watch the result and see what happens. And you could have done that experiment at home. If you did, then you probably got the same results where the book hit first and the piece of paper hit second. All right. So now what we want to do is we want to see is why does it happen? We want to explain how and why things happen in physics. So a lot of people say because the book is heavier, it hits the ground first. And for a lot of people, that is a misconception. That is not correct. So we have to try to explain what is happening. We'll kind of vary this scenario a little bit to show you that it does not have anything to do with the actual weight or the amount of matter in those objects, but we'll kind of look at that next. So let me skip ahead in the video here. All right, I don't want to do that. All right, so what we want to do, and what you should notice as it dropped, is that the piece of paper did not fall straight down, but it kind of floated a little bit, and that's because of the air resistance. So the air resistance affected the piece of paper much greater in a much more dramatic way than it affected the book. So what we want to do is try to eliminate this air resistance, and the way we're going to do this is we're going to crumple up the piece of paper. So we're not actually changing the mass of the piece of paper, we're just changing the shape of the piece of paper. So we have the book, and we're going to crumple up, and they're going to crumple up this piece of paper in the video. So you can see them crumple up. All right, and I want you to make another prediction as to which you think is going to hit first. If you think the book is still going to hit first, if the paper is going to hit first, or are they going to hit at the same time? So go ahead and do that now. And that's the result, and you could have done this at home again. The result is that they hit at the same time. So we want to explain that and talk about that. So that's where we're going next in this lesson. Okay, so that is a little introduction to free fall, and we did this. That's what we did here. So free fall is defined as when an object is moving under the influence of only gravity, and gravity here, the word gravity in this sentence that I highlighted in green means the force of gravity. So the only force affecting any object in free fall is just the force of gravity. We ignore everything else. So air resistance is not a free fall situation. Right? So examples of dropping an object or throwing an object into the air, they are examples of free fall. So it's a little misleading, the word fall. So like if I have an object here, So if I draw like a ball and this is the ground, if the ball is in my hand, and this is my hand, if the ball is in my hand, so if the ball is touching my hand, that is not free fall, right? So if it's in my hand, it is not free fall anymore. I'm trying to draw a better hand. Okay, it's not very good, but you get the idea. So it's touching, so there's another force acting it. My hand is holding it, so that is not free fall. As soon as it leaves my hand, so as soon as the ball is no longer in contact with my hand, it is in free fall, and the free fall will stop when it runs into the ground. So as long as the ball is above the ground, that is not free fall, but as soon as it comes in contact, it touches and is no longer free fall. We can take my hand and turn it the other way and put the ball, so there's my hand, and I'll change the color of the ball so it's a little easier to see. So we'll have a red ball. Okay, if I take that red ball and hold it in my hand that way, it's still not in free fall. If I throw it upward, all right, again, as soon as it leaves my hand, it is in free fall, and it will be in free fall all the way until when it goes up, and then it falls back down all the way until the ball reaches the lowest possible point right before it hits the ground. So we are only going to study the free fall part. So once it hits the ground, we don't really care what's going on. We want to know what is happening between when it leaves my hand until it hits the ground. The last possible scenario you could have with the hand and ball idea is sort of like dribbling a basketball. So if this is my hand, that's not a good hand still. But if I somehow took the ball and I gave it some initial velocity downward. So I gave it an initial velocity upward, gave it a velocity downward. This was just dropping it. So if I drop something, that means it's starting from rest. So again, the initial velocity in this case would be 0. This has a positive initial velocity, so a positive VI, and this would have a negative VI. And all of those are all free fall, at least in between the time period when gravity is the only force acting. So that is the key thing. Gravity is the only force acting on the object. Okay, so the acceleration due to gravity is a different idea. So we can talk about the force of gravity versus the acceleration due to gravity. The acceleration due to gravity near the surface of the Earth is a constant for all objects, and this is why those two balls hit, or the book and the crumpled piece of paper hit at the same time, because they experience the same acceleration. So if you think about the book, that's the book here, versus the piece of paper, they are definitely different masses. They definitely have different amounts of weight. If we put them on a scale, the book is heavier than the other one. But they have all the same kinematics ideas that are happening. So they're both starting at the same height. They are both starting from rest. The initial velocity of both of them is equal to 0. They're both falling the same distance. They both have the same acceleration due to gravity, which is constant on Earth. And it is a value of negative 9.8 meters per second squared. That's what we use for that. It's negative because gravity always tries to pull things downward towards the center of the Earth. But so gravity is the same. The initial velocity is the same, and the height is the same. So if all those factors are the same, the only thing that can happen is that they hit in the same amount of time. So the time for the book to hit the ground and the paper to hit the ground ends up being the same amount of time. And when we get into the problem solving part of that, of this lesson, we will discuss that as well. Okay, so so there are some assumptions that we will make with free fall that are slightly different than what we do with horizontal kinematics. So first off, if you drop something, the initial velocity is 0. Okay, so that's one assumption. Go to the next slide. So if you drop something, initial velocity is 0. When we're throwing something up into the air, when it reaches its highest point, which I call that point, I call that point the apex. That's a fancy word for high point. Other words that could mean the high point or apex would be like acme or vertex or pinnacle or peak, or climax. So all those words are just synonyms for the highest point, but apex is the word that I will use, and it stands out and makes people remember it. So at the highest point, the velocity at the apex is equal to 0. meters per second. And I want to show you this in a quick kind of just thought exercise. So let's say we had a ball, and let me extend this line a little bit and say this is the ground. And let's say we were going to throw this ball upward at 20 meters per second. And it's a positive 20. So positive 20 meters per second going up. And we said that the acceleration due to gravity g is negative 9.8 meters per second squared. 9.8 is the number that we're going to use in our mathematical calculations, but when we want to just estimate it, this is pretty close to negative 10. So I'm just going to say it's negative 10 meters per second, and I'm going to write it out the long way per second. So for every 1 second of time, we're going to add negative 10 to that velocity. So over here, I'm going to set a table up of velocity as a function of time, and we're at time equal to 0, and our velocity initially is a positive 20. And again, velocity is in meters per second with direction, whether it's positive or negative, and our time is going to be in seconds. Okay, and we're going to track the velocity at different moments in time. So at 1 second, 2 seconds, 3 seconds, 4 seconds, and maybe 5 seconds. We'll do all those. Okay, so and we're going to track the free fall idea. So it leaves my hand at 0 seconds. It's moving at 20 meters per second. If I think about I've changed 1 second of time, so I'm going to change the velocity by adding negative 10 to it. So if I add this acceleration value here, this negative 10 to my velocity, my new velocity is going to be going at positive 10. So that's the new velocity. So as it goes up, the object slows down, and that makes sense. So like you guys have experienced this in your everyday life. If you throw something up in the air, you jump up in the air, you slow down on the way up. So as you rise, velocity gets smaller. So it's still going up. It's got a smaller velocity, but if I go by another second and I subtract off another 10, kind of doing that change, and I'll be doing that change for all of these. When I go from positive 10 minus 10, I will get positive 10. Or I'm sorry, I'll get nothing. I will get 0, not positive 10. So if I have 10 and I take away a 10 or add a negative 10 to it, I get 0. So after my second of time, so this is at 1 second, this is at 0 seconds, this would be at 2 seconds. So at 2 seconds, or pretty close to 2 seconds, because this is an estimate, it's a rough estimate, we're not using the exact number, I am at the apex. So this is my apex when my velocity goes to 0. When I throw something up in the air, at the highest point is the apex, and that's when the velocity is 0. So just like everything else, once you throw it upward, it's also going to come back down. So that ball is going to fall back down. So as it falls, if I track the velocity over time, I'm going to keep adding that same change in time, or change in velocity for each second. So I've had a second of time. This is the third second. So 0 minus 10 is a negative 10. So it's on its way back down. It's going negative 10 meters per second, and that's at 3 seconds. If I do another second of time from 3 to 4 seconds, it's going to be going negative 20. And after that 4 seconds, it's going to actually hit. So I can't describe using these concepts. On the way back down, I have it in blue. I can't go past 4 seconds because that's when it returns to the original height that it's at, and that height was the ground level where it was launched from, or thrown from, or kicked from, or whatever it is projected from. So hopefully that makes sense, that the time up and the time down, they are essentially equal. So this is on the up part from 0 to 2 seconds. The down part is from 2 to 4 seconds. And the apex occurred at 2 seconds. So that's kind of an important fact. If you look at the shape, it is a parabola. And if you guys have studied some math before, parabolas, you can see are the same. So at different heights, it should be going, or if I'm at like the same height above the ground, they should be going the same velocity, just in different directions. So that's why it returns to the same ground at the same level. So it takes 2 seconds to go up, it takes 2 seconds to go down. It was going up at 20 to start, it's coming down at negative 20 when it reaches that equal level. Okay, so just talking about the equations and the math, the equations for free fall are the same as the equations for 1D kinematics with just a few subtle changes. So we change the gravity, the acceleration to gravity substituted in for A. So we use G for A, and G on Earth is always going to be negative 9.8. And then for X, we did horizontal motion. This is vertical, so it's Y. So we're going to change in Y. So if you look at these equations, they're all the same equations. We have our just small differences of X gets changed for a Y and A gets changed for a G. The steps in solving are also the same. So we'll pick this back up after this last question of ranking ideas for this situation. So for this situation, there are 3 identical objects, A, B, and C. They're balls, and they are experiencing free fall in different forms from the same height above the ground. So object A is dropped. Object B is thrown upward, and object C is thrown downward, and these 2 velocities are the same. So this is just a positive velocity, and this is a negative velocity. So I'm going to have you rank these, and I'm going to pause and let you answer these on the Edpuzzle. So the first one says rank these 3 objects in time order, so the amount of time they spend in the air, and we're always going to rank from big to small. So we're going to start with the one that spends the most time in the air to the one that spends the least time in the air. So here's your time to answer. And I think the correct order should be B, A, C. So B should be the most time spent in the air, A is second most, and C is the smallest amount of time in the air. And this just makes sense. So if you think about this, the one that spends the most time in the air is the one that's going to go kind of go the highest in the air. So B, we throw upward, so it goes way higher than A or C, so it goes up and comes back down, so that's more time. If we're dropping A and we're throwing C down, if you throw something down, it's going to take less time than if it's starting from rest, so that's the proper order for that one. Okay. Question B is a little bit tricky, and it says the speed with which they hit the floor. So if we had some sort of measuring device where we can measure how much speed each one runs into the ground with, that's what we're looking for. So let me pause and give you guys a chance to answer this one. So this one, when we're doing it, it's a little bit tricky because they're both positive and negative V. They have the same amount. So if you think about this, we said in the previous example where it goes up and comes back down. When it comes back down, it has the same velocity going downward that it started with when it goes up. So these are the same. So they're going to fall and continue to speed up. So this rank is a little bit tricky. It's B equals C. And then A is the one that has the smallest velocity because it goes the slowest because it doesn't have any initial velocity upward or downward to start with. Finally, the acceleration, you're supposed to rank from the largest acceleration experienced to the smallest acceleration experienced. So for this one, let me pause and you can answer the question. So for this one, they are all the same. So the reason why they're all the same is because the acceleration is equal to G, and G on Earth is negative 9.8 meters per second squared. Okay, so I'm going to stop there and we will pick up the last part of this lesson, which is dealing with solving free fall problems.